Hey everybody, and welcome back. If it's your first time here, welcome to this channel. I'm David Townsend. This is the Net Academy, where we are learning networks together. And on this week's video, what I'm going to be going through is something called generic routing encapsulation, or abbreviated to GRE. Now this is essentially a tunneling mechanism. It's a tunneling protocol that is not really new when it comes to enterprise networks and different types of networks. It's been around for quite a few years, but it's still used in networks today, and that's because it offers quite a few benefits and use cases as to when and where you would deploy and use a GRE tunnel. And on this video, what I'm going to be going through is, what is GRE? Obviously, what does it stand for? Generic Routing Encapsulation, already covered that. But when and where would you deploy or configure a GRE tunnel? What's the theory around it, of course? And what do you need to be aware of when it comes to GRE, those tunnels? So a bit of theory to begin with. It's always important to understand that. And then we're going to finish off going through how to configure a GRE tunnel. And I promise you it's so straightforward, very easy. So for now, let's get going with the theory and then build up to the lab from there. Okay, so let's start off with what is the GRE tunnel. Let's build up from there before we actually get to the lab. Let's start with the theory first. As always, it's important to know this stuff. Now, to answer what is a GRE tunnel, let me ask you the question. Do you know, or have you heard of a VPN, or virtual private network? They are different. GRE and VPNs are different, but the one similarity that I can think of is that they are both using tunnels. VPNs will have a secure, authenticated, etc. tunnel that's typically running from something like your laptop, your work laptop, just for example, over your Wi-Fi typically, and into the WAN over the internet to eventually it gets to a office location, a corporate branch location where the tunnels are terminated and the traffic comes out of it, and you get the resources and the applications that you actually need to do your day-to-day job. Now, when you look at a VPN, you've got this network in between the internet, all these different service provider networks, and that's really forming the underlay. The overlay, the VPN, is going over it. And as such, with this tunnel, you're bypassing, if you think of it in terms of a city where you've got all these traffic lights and roundabouts and all these other junctions, depending on the country you're in, you might call them different things. But when we've got this tunnel that's going over this service provider network, over this city, we're bypassing all those roundabouts, we're bypassing all those traffic lights, we're bypassing all of that traffic in between, and we're keeping it secure. And that is essentially what a GRE tunnel is doing. However, of course, there are a lot of differences between a VPN tunnel and a GRE tunnel. So the first point I want to start off with is that unlike VPNs, a VPN tunnel, GRE tunnels, generic routing encapsulation tunnels, they do not start and end from a laptop. They actually connect. They start from one networking device and end at another networking device. So when you've got your WAN routers, when you've got your routers sitting on the SD-WAN maybe, or some kind of networking device, a firewall appliance, a multi-layer switch, a router, that can form a GRE tunnel to another networking device. It's not from client, i.e. laptop, to a branch location. It's quite literally from, as you can see here, from one branch to another branch, from that branch to another branch, and from that branch to another branch. It's GRE tunnels connecting all of these sites together. But where and when would you actually use a GRE tunnel? Well, as I said at the beginning, they're still in use today. They've been around for a long time, and who knows how long they'll actually stay around for. But a typical use case that I could think of is where you've got a head office, a HQ, and you've got all these mini sites, all these mini branches that need to connect to that HQ, like a hub and spoke architecture, and they can then build those GRE tunnels to go over the underlay, over that internet, over that network, whatever that network actually may be, and connect all of these devices, and connect all of these sites together. Another use case of when you could use GRE tunnels, and this isn't to say that this is all of them, but another use case of when you could use GRE tunnels is when you've, say, got two sites which are separated by a huge network running RIP. So if you think of a network running RIP in the middle, and you've got two islands, two WAN routers sitting on the end, and they just want to have connections directly to each other, you could build a GRE tunnel to go over that RIP network, which is distance vector. It has a limitation of 229, 225 hop counts, something like that. It's been a while since I've touched RIP. But then you can make those two islands, those two routers, to feel like they're actually connected directly to one another. And another use case, and very similar to that, is say you've got a core network running IPv4, but maybe two of these routers at the access or distribution layer are running IPv6. You could connect them to those two islands together, those two routers together, using GRE, generic routing encapsulation. Because it's generic, it doesn't really care what it's encapsulating. It could be IPv4, it could be IPv6, it could be multicast, and as far as I know, pretty much anything else. It's generic encapsulation. So that, coming back to this example, allows those two routers, which are using IPv6, to form a GRE tunnel, to build that GRE tunnel over the IPv4 core network. And as I just said, this is generic. GRE, generic routing encapsulation. IPv4, IPv6, multicast, and a lot more. It doesn't really matter. It's encapsulation and de-encapsulation. So from a very high level, this is what GRE actually is. But how does GRE actually work? How does it build the tunnel? Well, down below you will see a diagram of a very simple network, and this is what we're going to be using in the lab in a few minutes time. On the left hand side you've got VEX, or virtual EX1. In the middle you've got VEX2, which is simulating that of the internet, that of a service provider network, and right at the end you've got VEX3. So really for this lab it's VEX1 and VEX3 that we're actually concerned with, that we're going to be doing the configuration on. But to allow connectivity, to allow the GRE tunnels to build and to actually work, of course they need some kind of IP addressing on that WAN interface. So if you look at the GIGI000 interface on VEX1, you can see that's configured to 200.10.20.1/30, and VEX3 has its IP address on its WAN interface as well, and the service provider has its IP addresses on its two WAN interfaces. And this is to allow global, as such, internet connectivity, isn't it? This is so we've got a routable IP address. And when we come back to GRE, what we're actually doing is we're building a tunnel that goes over this WAN connection, that goes over this WAN network, that actually extends from VEX1 over VEX2, the service provider network, and to VEX3 and back again. And to actually allow that configuration to take place, what you've got to have is a source IP address and a destination IP address for the tunnel. So the tunnel, because it's going over the WAN, over the network that's in between these two different sites, these VEX switches, it needs its own IP address, it needs its own broadcast domain. So we need tunneling information, and that sits on top of those WAN interfaces. So what you actually do is you define the tunnel, as you could see here, to have a subnet mask and an IP address that falls within the 192.168.10.0/24 network. And what you do when it comes to configuring, regardless of vendors, you say, what is the source IP address of this tunnel? And what is the destination that I actually need to get to? And what's important here is that that destination IP needs to be known. It needs to be advertised somehow. So if you look at the command line interface that I've done a snapshot on from VEX3, you can see that the GR tunnel, the GRE tunnel 0010, has been configured with a tunnel source of 200.10.20.6. That is the GRE 001 interface on VX3. But the destination IP address of the tunnel is 200.10.20.1, which is the GRE 000 interface on VEX1. But also the family INET is that of 192.168.10.3, the .3 being for VX3. So the point here is that the GR tunnel is referencing the IP address of the WAN interface on GRE 003, and it's saying, well, this is where I'm going to build a tunnel from, and this is where I'm going to build it to. And coming back to the point that this needs to be routable, if you look at it from VEX3's perspective, the destination for the tunnel is 200.10.20.1, which is the GRE 000 interface on VEX1. But it doesn't have a direct connection there, and it might not know how to get there initially. So you need some kind of routing protocol to say, to get to 200.10.20.1, I need to go out of this interface, or I need to go in this direction. Now what I've done in this lab is actually define a static route, and you'll see this, but I've defined a static route to say, well, to get to 200.10.20.1, my next hop is 200.10.20.5, which is the VEX2's connection to VEX3. But this is absolutely, regardless of vendor, the minimum configuration that is required. And because we're tunneling over the service provider's network, tunneling over VEX2's network, it's completely transparent. It doesn't see this GRE tunnel. It just doesn't see this tunnel's source and tunnel's destination IP address. But why is it transparent? Why did I just say that VEX2 cannot see the packets belonging to the GRE tunnel and the inside information? I'll come on to that. That is because, and I've said it just a few minutes ago, that there is this concept of underlay and overlay when it comes to VPNs and when it comes to GREs and eVPN routing and quite a lot more. And from VEX2's perspective, it's providing the underlay, it's providing the connectivity between VEX1 and VEX3 from site 1 and site 3, from a branch site to a HQ. It's providing the WAN connectivity, it's providing the internet connectivity, it's providing the underlay connectivity. And because it's providing the underlay connectivity, it doesn't see the GRE tunnel that's built on top of it. And what's built on top of it is, of course, that GRE tunnel with that 192.168.10.0/24 family INET, the IP addressing and this source and destination. But it doesn't see it because that's what's known as the overlay. So really the underlay is carrying the overlay traffic. And when it comes to GRE, generic routing encapsulation, the GRE is encapsulating new header information on top of what's already there. So what's already there? You are going to have a payload. Doesn't matter what's in the payload. That's obviously the data. That's the application that needs to be used. Payload could be whatever, quite literally could be anything. And then you're obviously going to have a source, destination, MAC address, etc., etc. I haven't put that on here for obvious reasons, but there's going to be an inner IP address, an inner IP. And what GRE is doing is it's adding its own little bit of information, its own little bit of header, and that is the GRE header. Come on to what that actually does in just a few seconds, but that is the GRE header, and it also then adds an outer IP header, both source and destination. So from right to left, we've got the payload and the inner IP, both source and destination. And when it starts to be built, when these packets start to or need to go through a tunnel, GRE adds on a GRE header and an outer IP source and an outer IP destination IP address. And when it gets to the other end, so from VEX1, packet comes in, needs to go to VEX3, encapsulates it with GRE and an outer IP header, and when it gets to VEX3, boom, VEX3 strips off that outer IP, the outer source, the outer destination IP address, takes away the GRE header, and then it's left with the original packet, the original inner source, the original inner destination IP address, and the payload, of course. But when it comes back to what are these two headers that are added to this original packet, first the outer IP. Now that is what's used to transport those packets across the underlay. So this would be the overlay IP addressing. So the outer IP is that of the WAN interfaces in this example. So if we look at it from VX1 and we want to send a packet from VX1 to VX3, the outer IP source would be 200.10.20.1 and the outer IP destination would be 200.10.20.6. Now the GRE header adds a bit more information to it. It says, yeah, this is what I'm encapsulating. It's IPv4, it's IPv6. There's an aspect of an authentication key. There's a checksum, there's flags. Quite a bit of information that goes into this 4-byte header. But that's generically, generic no pun intended, what GRE header is providing. And then you've got the inner IP, and that's used as the overlay signaling, the overlay IP addressing. So that would be, I need to get from the LAN interface 172.16.100.1 on VX1, and I need to get to the destination IP of 172.16.200.1 on VX3 from one LAN to another LAN. And it's transparent because all VX2 sees is that outer IP. It only sees that outer GRE. It does not see the inner IP information. And thus, when you do a trace route on, as we will do on VX1 to VX3, when it goes through the GRE tunnel, you won't see the IP addressing on VX2 or even on VX3's WAN interface. You'll just see them as directly connected from the LAN interface, the 172.16.100.1 on VX1, and directly connected to the 172.16.200.1 on VX3. And just to put that into a little bit more technical perspective, this is a packet capture that I'd done on the lab. I generated a trace route or ping from VX1, I think it was, to be honest, to VX3, and you can see there's quite a few packets there. There's OSPF, ICMP, there's the initial ARP requests as well. But then when the response comes through, we get that header information, as you can see on the bottom left. Now, just focusing in on that, what you can see is that the first Internet Protocol version 4, the IPv4 addressing, the source is 200.10.20.1. That is the GIGI 000 interface on VX1, and the destination is that of 200.10.20.6, which is the GIGI 001 on VX3. So this is the outer IP address, the outer header. And then there's the GRE header, and then there's the inner payload, the inner IP address. Shouldn't say payload, but the inner IP addressing. So you could see here that the source was coming from 172.16.100.1, and the destination was going to 172.16.200.1, which is the LAN interface on VEX3. Why Wireshark is showing it in a different order, honestly, I don't know. But absolutely, with 100% certainty, the outer IP is the first one that's shown here, the 200.10.20.1 or 20.6. That is the outer IP. And then the inner IP is shown as the second IP addressing in this packet capture. It's just how Wireshark works. I would think it would be in a different order, but you know, Wireshark is Wireshark. But there are some points that you need to be aware of when it comes to generic routing encapsulation. First off, one of the points, and there are quite a few points, but I want to go through my top 3 or top 4 points, is that you have to be aware of the interface state. If the remote end goes down, if the remote endpoint of the tunnel goes down, it goes from an up to a down state, then the local end of that tunnel is absolutely unaware of it. And therefore it is stateless. The nature of GRE is that it doesn't know the connectivity. It just assumes the connectivity there and the remote end is there and working and functioning and up. So if the link goes down at the other end, the local end doesn't know, and you can still send packets, as far as I'm aware, over or through that tunnel, through the overlay tunnel. The other point to be aware of is that it is unidirectional. In the lab, it's not good enough just to configure VEX1 for GRE tunneling. It has to be done on VEX1 in direction A to B, and it also has to be connected and configured on VEX3 for direction B to A. It has to be done in both directions. The other point, and you read a lot about this, is this concept of the maximum transmission unit and the maximum segment size. This is basically something you do need to be aware of, because GRE, just like any protocol, has or will have header information, and the header information uses and will have a particular byte size, a size of bytes. Now the difference between MTU and MSS is MTU is the packet, the whole packet, including payload, source destination IP addressing, protocol, etc., literally every header going on the IP, TCP, UDP packet is including all of the header information. MSS, on the other hand, maximum segment size, is actually referring to just the payload itself. So the MSS is always going to be smaller in bytes than the MTU, because the MTU takes into account the overhead, the MSS absolutely does not. And the problem with the MTU and MSS is that the typical standard configuration, regardless of vendor, is 1500 bytes MTU, which is about 1460 bytes MSS. Obviously, again, there's a difference there. Now, GRE adds in certain two overheads, two parts of this overall header. You've got 4 bytes for the GRE header, as I showed on the last slide. That is 4 bytes where you've got the key and you've got the checksum and maybe some flags. But then you've also got 20 bytes for the outer IP. So that's 24 bytes in total. Now this is important because if you don't take the MTU and the MSS into account, then you can get packets suddenly which are coming through which are too big in packet size for the MTU that's been configured. And if that router is configured to do not fragment, it's got no other choice but to drop those packets. If it's configured to do not fragment, i.e. these are coming through, they need to be fragmented, then you can fragment those packets, but that's not ideal. You want to avoid either one of those scenarios. So you do need to take this into account. But here's the quick maths for you without scaring anyone away. So the payload from a layer 3 perspective is 1460 bytes. And we're almost talking about jumbo packet sizes here. And then you add on the 20 bytes at least of the TCP header, and then the 20 bytes of the IP header, the inner IP that is, and then the 24 bytes of the GRE header and the outer IP header, which GRE adds on, then suddenly you've got 1524 bytes. So originally starting with 1460 bytes for the maximum segment size, it will then be 1524 bytes, which is way over the MTU, which is configured by default to be 1500 bytes. Now that's what you need to be aware of, because again, if the routers are configured to do not fragment, then it will drop the packets. If they allow fragmentation, then that will slow down the delivery of packets, could cause congestion, etc., etc., etc. So that's why I say in both scenarios, you need to be aware of the MTU and MSS. Okay, here we go. Here is the lab. Let's configure VEX1 to build the GRE tunnel to VEX3 over the service provider network, that is VEX2. So let's go onto VEX1 just to begin with, and I'm already logged in, and I just want to show you that I do not have any tunnels configured. There's no GRE tunnels configured, and actually if I just do a show interfaces, I've only got the GIGI 000 interface, which is configured already for the WAN, for the 200.10.20.1/30. So what I should be able to do is actually do a run ping 200.10.20.2 which is the WAN interface on VEX2, the GRE000 interface. And of course I get a ping response from that. I get an ICMP response, a reply from that. But can I actually ping all the way across over to VEX3? So can I ping the 200.10.20.6 on VEX3? And no, I absolutely cannot. And that is because I don't have a static route or a routing protocol that is advertising and letting VEX1 know that, if you want to get to VEX3, this GRE001 interface with this IP address ending in 20.6, you can go through me. So if I just do a run show route, and if I spell it correctly, you can see that the 20.6 is absolutely not here. So Simple Lab is a simple network. The 20.6 or the 20.4/30 network is not in our routing table. Now, what can you do to resolve this? And this is important because we need this underlay connectivity to allow GRE tunnels to be built. What you can do is just do set routing options static route, and to get to 200.10.20.6, the next hop to get there is 200.10.20.2. That is the GRE000 interface on VEX2, the service provider network. And now if I commit that, that ping should then work. So if I come back and do the run ping 200.10.20.6, I now get a response from VEX3. So that underlay connectivity is absolutely there. Now, how do you define the GRE tunnel? Remember, you need a source, you need a destination, and you have to define the IP addressing on the tunnel as well. It's a tunnel, it uses IP addressing, it's got to have IP addressing to build the tunnel. That's got to be configured. Now to do that in Juniper Junos, just do set interfaces GR. You don't define GRE. I don't know why it's not GRE, to be honest, but GR 0.0 in this particular case, and I'm going to do 10. Honestly, it should be 0, but it's vJunos. I think there's a weird bug here that I need to use GR0010, but this should reference the physical interface, in this case the GRE000, but it's a virtual lab, it's free software, it's a free image, and I think in this case it's a little bit buggy, to be honest. But set GR0010 unit 0 or dots 0, and now if I hit question mark and let me expand this, you can now see here the tunnel parameters. And notice well we could do the family, which is where we're going to define the 192.168.10.0. But first let's just do tunnel, hit question mark, and I could define the source. The source is going to be the GRE000 interface, the IP address of 200.10.20.1. I can now define the destination. The destination is going to be the GRE001 interface on VEX3 that has the IP address of 200.10.20.6. Now if I just do show interfaces GR0010, you can see that I've got the source, I've got the destination. But if I just hit up, there is also the family INET that's missing. I have to define family INET to have the IP address of 192.168.10.1/24. The .1 being for VEX1, VEX3 has 192.168.10.3, falling in this /24 subnet. That is, oh, I forgot the address, so let me just hit back. That is, do show interfaces GR. That is the GRE tunnel configured. I'm not saying it's up, but that is it actually configured. Now if I do quick commit, can I get from 172.16.100.1 on VEX1 to the loopback address on VEX3 of 172.16.200.1? Well, actually no, because what I have forgotten to do is I've forgotten to configure the loopback interface. So let's do that first. Let's do set interfaces loopback 0. So there's not actually a LAN connected to VEX1. I'm going to use a loopback address to simulate that of a LAN connection. And let's do family inet 172.16.100.1/24. I've done it again. I keep missing the address. Address 172.16.100.1/24. And let's commit that now. Now the question is do I have connectivity from the LAN on VEX1 to the LAN on VEX3? Well, let's do run ping 172.16.200.1 from the source 172.16.100.1. I am going to ping VEX3's LAN address from my own LAN address. And absolutely I do not. Why is that? Because if I do run show root again, we don't have 172.16.200 in the routing table. So that obviously needs to be changed. So what do? Let's define the routing options again, a static route. Remember, this is the big part. To allow connectivity, you need routing knowledge. You've got to use some kind of routing protocol to let, in this case, VEX1 know if you want to get to this destination, this is the path you need to take. But I'm going to do next hop 172.16.200.1, next hop of 200.10.20.2. And let's commit to that now. And with that committed, let's do a run ping. Actually, let me hit up. Okay, and with that now committed, if I hit up a few times, and let's run that same command, run ping 172.16.200.1, the LAN interface on VEX3 from my own source, my own LAN interface 16.100.1. Now, so this should work, and I do actually get a response at this point. But what is the problem here? Well, if I do run traceroute 172.16.200.1 from the source 172.16.100.1, you can see that actually we see the underlay. The first hop IP address is 200.10.20.2. That is the GRE 000 interface on VEX2. So basically, to get from the LAN on VEX1 to the LAN on VEX3, it's not going over or through the GRE tunnel. And this comes back to your routing policies. If I do show routing options, what I've defined is to get to the LAN interface on VEX3. Actually, I want to go to VEX2. I want to get to this next hop IP address. And this is why we're seeing this traceroute not using the GRE tunnel. So that needs to be changed. That actually needs to say next hop GRE tunnel 0010. The GRE interface we've actually configured right here. So what I would do is I would delete that routing option static route to 172, etc, 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 and I will set the routing option static route to get to that LAN interface of 200.1. Then the next hop to get that is that GR0010 interface. Now if I do a quick commit on this, and with that now committed, if I do the run ping, actually let me hit up, let me see if it's still there, and there we go. Do I still have connectivity? We do. But now let's compare the before and after. Let's compare, do we now see the underlay? Is this traffic going from one LAN to another LAN, hopefully through the GRE tunnel, is that transparent? Is that not seen, I should say, by the underlay? Do I not see any of the underlay IP addressing? So let's do that run traceroute command again. There we go. So run traceroute from LAN 1 on VEX1 to the LAN on VEX3. And note now the absolute difference. To get to 172.16.200.1, it just looks like it's directly connected, doesn't it? It didn't see the 200.10.20.2. And if I scroll slightly back up, you could see right here, that's where it is. That's what it was before. So in summary, it is very, very easy to configure GRE tunnels. In this particular example, we are using a loopback interface, loopback 0, to simulate that of a LAN address. And we are building the GRE tunnel using the GRE 0010 0 interfaces that IP address and the destination of the GRE 001 interface on VX2 as both the source and destination respectively. And we've also defined that the IP address for the GRE tunnel on VX1 has this 192.168.10.1/24 IP address. So configuring the GRE tunnel is straightforward, as you can see. But what will throw you off is if you do not have your, in this case, static routes configured correctly, or if you don't have that routing protocol to actually advertise this LAN IP addressing. So what we did have to do is, yes, say, to get to the GRE 001 interface on VX3, to get to this IP address, I need to go via VEX2. But when I want to get to this LAN on VEX3, this 172.16.200.1, I need to go through that GRE tunnel. Now I'm just going to play about with this right now. Let's see if we can configure, coming back to one of the use cases, say VX2 is running IPv6 and VX1 and VX3 are running IPv4 as they are right now. Can we build an OSPF adjacency from VX1 to VX3 over the VEX2 through that GRE tunnel? So let's do it side by side. So let me just bring up VEX3 and VEX1. So all I'm going to do very quickly is just do set protocols area 0 interface GRE 0010. And let me do the same on VEX3. Let's do set protocols OSPF area 0 interface GR 0010. And let's commit both these configurations. And with good old OSPF, might take a few seconds to come up, but let's just do a run show OSPF neighbor. And you can already see the state is full. That's basically the BGP equivalent of established in both worlds. That means I have full neighbor adjacency. It's up, it's good. And we can actually see, note 192.168.10.3. That's very interesting actually. That is the source tunnel IP addressing 192.168.10.3 on VEX3. And it's built the adjacency from VX1 to VX3 through that GRE tunnel. It's one of the use cases right there. But always remember, before I close the lab down, that it needs to be done in the opposite direction, but in reverse order. So this is VX3's configuration. So what I defined on VX3 is the same GRE tunnel, but its source is 200.10.20.6, the GRE 001 interface on VX3. The destination of the tunnel is 200.10.20.1. That's the GRE 000 interface on VEX1. It's got its family INET addressing, and if I just do the show routing option static, obviously it's got its static routes configured as well. So to get to that GRE 000 interface on VX1, I need to go via service provider router, VX2's interface right here. And when I want to get to VEX1's LAN, that 172.16.100.1, I need to go through the GRE tunnel. Remember, GRE is, yes, stateless, but it needs to be configured in both directions. So there we go, everybody. That is the end of this video. That is the end of GRE, both theory and a quick lab example. In summary, GRE, generic routing encapsulation, it is a generic encapsulation and de-encapsulation of a lot of underlay traffic, IPv4, IPv6, multicast, like OSPF, encapsulating it with two different headers, the GRE header and the outer IP header, and then tunneling all of that traffic over the underlay, an overlay routing tunneling protocol to where it gets to the destination, and then is de-encapsulated. The GRE header is stripped off, the outer IP header is stripped off, and then that inner IP and that payload is nicely there. We also went through the use cases, a few use cases of when and where you could use GRE. And as I said, GRE has been around for quite a few years. It's still in use in networks today, and I don't foresee it's going to disappear anytime soon. And then we went into the lab. How quick and easy is it to actually configure GRE? Very straightforward. You need the source, you need the destination. They've got to be known, especially the destination. It's got to be known. You've got to have a static route or some IGP or EGP routing protocol to say, yeah, this is how you get to that destination. And then what we did is we compared the trace route before GRE was actually working and then done the same trace route afterwards, and you could see that actually, suddenly it is transparent. The underlay doesn't see this IP addressing. It only sees the outer IP and not even the inner IP. So very interesting stuff. But don't forget about that maximum segment size, that maximum TU, that maximum transmission unit. Got to take that into account. But I hope you found that useful. Hope you found that informative. Any questions or comments, let me know down in the comments box. I love hearing from you all. Other than that, thank you for watching and goodbye.